Sorry about this. We had this problem before as well. Mm. Okay. Is the resolution fine or? I'm duplicating. Oh, so I think the resolution is wrong. Mm. It's all right. Oh yeah, it's off. Okay. Okay. This should work now. Okay. Oh no. Does anyone have any idea what? I have no idea what's happening here. So do you mind actually let's full screen this because I had this slideshow up to here. Oh no.
Doesn't want to go into the right.
Yeah, I have no idea what the problem is. Should I restart?
No, just give me a sec. Okay, let me try this one more time then.
Okay, thank you so much. All right, after some technical problems. So first, I would like to thank the organizers to give me the opportunity to give a talk with a title like this. That probably sounds like gibberish to most of you guys. But there is an informal title. So this talk is going to be an invitation to information theorists to think about gravity. This is work with, in collaboration with Bartek Czech, Patrick Hayden, and Brian Swingle. All right. So I'm a physicist, and from the point of view of physicists, we typically like to divide or classify natural phenomena based on the energy scale and temperature where we observe them. So for example, down here, if the temperature and energy scale is sort of low, systems could be prepared in laboratories. Then there's a framework of condensed matter systems. And if you go a little bit higher energy, for example, collider physics or early universe, we have quantum field theory. And at very, very large energies where gravity is important, we have quantum gravity. Turns out quantum information theory is actually useful to all these three fields. So you're probably familiar with this part, the many-body entanglement, and the role is played in understanding or partial understanding the ground state of strongly coupled systems. But then this slide is not to intimidate you, but actually to tell you that there is actual applications that people are actively working on. And quantum information theory has been very, very useful in both of these two other energy scales. In particular, this talk is going to be mostly about this side, which is the highest energy scale and quantum gravity and the application that it has. So just one important comment here is that I'll try to advocate the point of view that quantum information theory and quantum gravity is more than an application. It's actually some of the concepts in quantum information theory are going to be fundamental for understanding gravity. So as we go along, I'll explain what I mean. So I'll start with a 5-minute version of my talk, and I'll try to explain to you all you need to know to follow this talk, hopefully. So what is the question we're studying? Sorry, what is the field that we're studying? what are the questions we're after, and why we think information theory can help. So here's what we're studying in one sentence. It might look scary, but I'll walk you guys through it. Quantum gravity in negatively curved space-time is what we're studying. So what you need to know for this talk is that it's quantum, so there's a Hilbert space. All right, that's familiar. It's gravity, so it means that there's a sector of this Hilbert space that has some effective simplified dynamics, that's classical, by some equations. They happen to be Einstein's equations, but there's some classical dynamics, simplified dynamics, that captures this sector. And it's in negatively curved spaces. What does that mean? It's really this simple intuition of spaces being either flat, positively curved like a sphere, or negatively curved like a saddle. And I'll explain a little bit more, but you don't really need to understand much about it. You might ask me why we're looking at negatively curved. The honest answer is that that's the only case we understand quantum gravity, and the two other cases are extremely complicated. Actually, we happen to have a non-perturbative definition for quantum gravity in negatively curved spaces. All right. Then there's jargon. This one line usually goes with this short form, ADS-CFT duality. Of course, I'm hiding a little bit here, but that's okay. The term duality means something important here. And that's the fact that here I told you that there's a Hilbert space. This Hilbert space happens to have two different physical interpretations. The same dynamics, same Hilbert space, has two different interpretations. One in the language of gravity, the other one is in the language of a non-gravitational theory. It happens to be a quantum field theory, another set of theories that we love and we study. So a huge amount of effort in my community goes into understanding the duality dictionary. We have one Hilbert space, two different interpretations. What is the map that takes gravity concepts and objects to the other side that's non-gravitational? And finally, why information theory helps. There are many, many different ways of motivating this depending who you talk to. For the purpose of this talk, I would like to make this connection, that it turns out that most of the times when we try to understand what geometric quantities map to under this duality, we find that they are mapped to some sort of entropic functions that are quite familiar in information theory. Quite often they're pretty complicated ones and we don't really know what they are, but they're entropic functions that should sort of look familiar. All right, that's the intro. I'll go through it slower. But what is new? So what am I presenting? What's the result that I'm presenting? We think we have a new entry in this dictionary. In particular, we connect the length of curves on the gravity side to some entanglement cost of a communication protocol that we call streaming compression. And I'll conclude. All right. So slowly from the beginning. So gravity in negatively curved space. So this is a negatively curved space, as I said, is really like a saddle. You can think of that as what it looks like. This is a hyperbolic disk. These lines that I'm drawing these semicircles, they are straight lines, or geodesics as we call them. So a free particle moves along these lines. You can see that I can make a triangle with three of these quote-unquote straight lines, and it will have the sum of angles around the triangle is going to be less than 180 degrees, hence we call it a negatively curved space. Most of what I say here generalizes to higher dimensions, but for the purposes of this talk, for simplification, I'll just talk about 2D so that I can draw pictures. So one important thing is that we usually say ADS, or anti-de Sitter space. That's nothing really fancy. It's just this hyperbolic disk times time direction. And because most of what I talk about today is time independent, you don't really need to worry about that. But if you want to know the jargon, that's roughly speaking what it is. Then there's one thing that you need to know about ADS, or hyperbolic space, that physically this thing is like a box with walls. Why is that? Because if you stand in the middle or anywhere in the inside and take a laser pointer and point it at any direction, this laser beam will reach infinity and bounce back and reach back at you in finite time. So it's like a wall. It's like a box, right? It's like a finite box. It's some sort of geometric construction of finite box. So what does that teach you? It teaches you if you try to construct a physical theory in this space, you need boundary conditions at infinity, which is the outermost circle. So I'll use this a little more jargon. Boundary versus bulk was inside the disk. All right. So I told you this is a theory of gravity. So I told you there's a Hilbert space in here. So what is a Hilbert space? The vacuum is just simple, plain hyperbolic disk. Excited states are just throw in particles and massive, like particles in the middle. And those are going to be excited states. So it's a theory of gravity, which means that the presence of particles actually changes the metric, will deform geodesics. As you see, this was used to be, the green curve used to be a straight line. In the presence of matter, it's going to get deformed, according to Einstein's rules. But we don't really care about that here. All right. So ADS-CFT duality, just repeating what I just said, but in more formal terminology. I'll try to be quick. It's the same thing. So you took the hyperbolic disk times time. So there's a theory that lives on the boundary. It's ignore what CFT is, doesn't matter. It's just some non-gravitational theory. That's all you need to know. That lives in one less dimension because it's on the boundary of the disk. And inside the bulk, there's a gravitational theory. There's a lot of jargon here, but if you're not familiar with it, just don't worry about it. And this is to say that there are examples. If you don't know what it is, doesn't matter. We have millions of examples. We actually have many examples with free parameters, so it's not really important. But this is the intuition that was formulated by Maldacena back in '97. That every time you try to, it seems like every time you try to make sense of quantum gravity or string theory, in this space, it always happens to have this property. One Hilbert space, two different descriptions, one gravitational, the other non-gravitational. And that is what's called ADS-CFT duality. So in this talk, we're going to be after finding dual or the map from the geometric quantities in the bulk to the boundary. What are geometric quantities like length and curvature of curves in this simple picture? And as I advocated before, this is the intuition. If I have time at the end, I'll tell you a little bit more about why we have this intuition, but let's not worry about that for now. Okay. Before I can actually talk about what we've done, I have to tell you a little bit about the basics of the map that we understand. There are a lot of things about the map that we don't understand, but let me tell you about the things that we do understand. I told you that earlier that states on the boundary theory, non-gravitational theory, that correspond to geometry and matter fields in the bulk. So particles and geometry, and that's what the essence of duality is. One more thing that's going to be important is the following thing. So the bulk theory has one extra dimension. So you might ask yourself, how is that extra dimension manifest in the boundary theory? It happens to be that, okay, so let's see. Oh, okay, all right. So it seems like this space, hyperbolic plane, has the property of, it has some sort of rescaling symmetry. It means that if I go near the boundary, take this triangle and resize it and pull that thing more inside, it's going to look the same. So there's some sort of rescaling symmetry of this type, that I'm changing R and changing theta, and it's the same sort of space. All right. So it suggests that the phenomena that correspond to slowly varying physics correspond to whatever happens deep inside the bulk, and the things that are like high frequency, quickly changing physics is related to near the boundary. I don't know why this pointer. Oh, this is on the way. Okay. All right. So second point in the dictionary. So I promised that there is some connection with entropic measures. So this is the connection, at least the first one that I'll talk about today. It's a very important one for us. It was conjectured back in 2006 by these two gentlemen, Ryu and Takayanagi, that one of the entries in this dictionary works this way. You take a subsystem of the boundary theory, say A, and you calculate its entanglement entropy. You're familiar with this. This is von Neumann entropy of that state. And that entanglement entropy is dual to the following quantity. So I wrote area because that works in all dimensions, but for the purposes of the picture I've drawn, it's actually length. So it's take all curves in the bulk that end on the endpoints of this boundary region and look at find the one that has minimal length, right? So this is gonna be, some of them are gonna have longer length. There's one that has minimal length, and in this simple case, it happens to be the geodesic. And the answer is this simple. Entanglement entropy of the boundary is the length of that geodesic multiplied by this number. It's a fixed number, it's a Planck constant. It's just some number. All right, for the people who know a little bit about black hole physics, this generalizes as black hole entropy, but that doesn't matter. You don't need that to understand this talk. And this is just to give you an impression of, so originally it was actually shown in 3 dimensions, then people checked a lot of non-trivial, did a lot of non-trivial tests, and eventually, like as is usual in our field, this guy Maldacena comes along and proves it. So he proved it in 2013. It plays an important role for us, and to just tell you how important it is, it was awarded the New Horizon Prize in Fundamental Physics. These 2 gentlemen got it recently. All right. So let me just go slower, actually. So I want to reinterpret this in a language that you guys are familiar with. I'm telling you that the length of a curve is mapped to entanglement entropy. So what is entanglement entropy from the point of view of an information theorist? What's the interpretation of it? So typically we think of entanglement entropy as some sort of, in the language of some communication language, there's Alice who has access to this part of the boundary. There's some state, Alice has a state and wants to pass that state along some channel to Bob, right? So what does she do? She compresses it and sends it over in quantum communication, and this is the amount of quantum communication she needs, right? The second interpretation is the same thing, but by teleportation. So what they do is that they teleport this state, but in order to achieve such a thing, they need a minimum number of entangled pairs that to have that entanglement present between the 2 of them, and they use up that much entanglement, which is given by von Neumann entropy. All right. So here's our new result. What we're going to do is that we're going to generalize Ryu-Takayanagi, that conjecture, or actually the result that I just presented to you, to arbitrary curves. So what we're going to do is that previously there was a minimization over all curves. We're going to generalize that to all curves, and we're going to talk about the same communication, well, a similar communication protocol. So this is what the promise is, length of arbitrary curves. It's not really arbitrary, it has to be convex, but that's for some technical reason. It's going to be long to discuss. But anyway, so what is this communication protocol? So let's say Alice is sending the state to Bob, but Bob is impatient. So Bob doesn't want to wait until Alice compresses the whole thing and sends it over. Bob wants to, as Alice is compressing, wants to receive the state. So Alice is going to stream the state to Bob, right? So just to give you the upshot, the new entry in the dictionary that we're suggesting is the following thing. There's a correspondence between the length of an arbitrary curve and the optimal entanglement cost of some communication protocol. It's called streaming teleportation that Alice and Bob perform. And these are, I put references from different places. All right, so this is what's going to happen. Let's go back. So what's going to happen is that Alice is going to start with a part of the boundary, the state that she has, locally compresses it, pass it along, move a little bit further, local compress, sends it along, and how much access she has to local data, we're just like following some rules. At this point, she has this much to compress. All right. So as usual, if you want to explain something in simple terms that are familiar, you have to connect it with your everyday experience. In North America, Netflix is an everyday experience. So imagine Netflix is Alice and you're Bob, and Netflix wants to send you a movie, right? So the best compression rate is achieved if you wait until you download the whole movie and then watch it. That's the best compression rate. It explores all sorts of correlations between different, like short scale correlations, and also long scale correlations from the beginning and end of the film. But our protocol is different. How is it different? Streaming compression, meaning that you just have access to you can only locally compress. You cannot really use long scale, long range correlations. So that's how we're going to compress. All right, so what does this look like? Here is some curve. It's sort of close to a boundary. At this point, we start, Alice can use this much to compress and sends it over. At this point, this much, this point, this much, and so on and so forth. So when the compression, if you want to stream really fast, you're impatient, so you have to use only short scale compression, high frequency. The curve stays near the boundary because I told you that there's a connection between scale and how deep in the boundary you are. The bulk you are, sorry. This is not efficient, obviously, because you're not exploiting the correlations that exist at all scales. But the pro is that you start watching right away. That's the positive side. But if you allow this to have a little bit of lag, so you start exploring higher and higher range correlations, this starts exploring deeper and deeper in the bulk. So you allow Alice to compress at larger scales, and you go along. This is becoming more and more efficient, and at some point you allow Alice to use all frequencies. And in that case, what she's doing is that she's just compressing the whole thing and sending it to you, which we already know has it reaches deepest in the bulk, it's the most efficient, and it's actually the minimal curve and entanglement entropy, the Rio-Takayama result that we already had before. All right, so this is the story. Just to explain a little bit about what is happening, so let's go back here. No, actually. All right. So again, I come back to this picture. Alice is sending it to Bob. At each step, what is happening is Alice is locally compressing it and sending it along. So at each step, it looks like a state merging protocol. So Alice has access to a little bit. Bob has access to a little bit more, some local constraint, and she wants to pass it to Alice. The cost of such a teleportation protocol is actual conditional entropy. This was shown by these gentlemen back in 2005, I believe. This provided an interpretation for conditional entropy, and it made it really pleasing because previously we didn't have an interpretation for conditional entropy in quantum mechanics. All right, so in our protocol, what's happening is that the cost of this, we actually have shown this, but I'm hiding this. I'm not going through the details. The cost of this process, okay, no. Oh, I think the animation is not working. Anyway, so the cost of this process of this streaming teleportation is going to end up being sum of a bunch of conditional entropies, and we prove that this is actually nothing but the length of the curve in the bulk. So, okay, so here's the lesson. The length of a convex curve is the minimal amount of entanglement that Alice and Bob need to perform such a streaming teleportation task. So, of course, you as a crowd, information theorist crowd, you want to know if this is optimal. We proved optimality of such a thing, such a rate. And furthermore, another thing that you might worry about is whether this is a one-shot result. Turns out this came as a surprise to us as well. But in the class of theories, we're interested in, this H max is always a good approximation for conditional entropy. So it worked perfectly. This is a result, by the way, in 1 + 1 dimensional conformal field theories with large central charge. For people who want to know what this result comes from, the large central charge plays an essential role here. Those are the theories we believe have gravity duals, but that's just some technical comment. All right. Oh, now the animation is working. Too late. All right. So this is my last slide before concluding. How much time do I have?
Between 5 and 10 minutes.
All right. So this is my last slide. So in this last slide, I want to convince you that it's a good idea to think about gravity. And as I said earlier, quantum information theory and gravity physics is more than a tool. It's actually an essential thing we need to understand gravity. So this is what I'm going to try to sell to you guys. Gravity is a quote-unquote thermodynamic theory of space-time. So what the hell does that mean? So I told you that we are studying theory of quantum gravity, some Hilbert space that has a low energy, has a particular sector that's described by gravity. No one told me that theory is unique. Indeed, we know that there's a zoo of such theories that have all of these guys. If you go to long wavelength and you allow this large number of modes, they have this universal simplified sector that's described by gravity. These are very complicated quantum theories. They have really, in terms of microscopically, they are very, very different, but they all have that limit. that should ring a bell from your early education in physics. We have a lot of different theories, but somehow when you go to a long wavelength limit and you allow a lot of excitations, you just generically find some effective thermodynamic behavior which is universal and simplified. So this is the sense in which I want to say gravity is actually a thermodynamic theory. So this was actually mentioned, this was observed by earlier on when people were starting to talk about quantum gravity, people like Hawking and Bekenstein, and they started, at the time they were formulating laws of black hole thermodynamics. They found a similarity between thermodynamics and gravity. But now we know that this similarity is actually this connection is actually has a larger, I guess, is more concrete. So it doesn't matter if you understand what these quantities are. I just want to tell you that there is a well-established map between these guys, things you understand from thermodynamics and things that we understand are familiar from gravity. One more thing that I wanted to tell you is that, okay, no, maybe I'll wait for the conclusion. So this is the point I was trying to advocate. It seems like all that gravity cares about is something like some averaged long-range properties of a lot of degrees of freedom. So to conclude, we discussed how bulk geometry and boundary entanglement are intimately connected, and then we tried to find a connection between compression and length of curves, the rate of compression rates and length of curves, and in particular we're talking about arbitrary curves in 3 dimensions. Actually, I didn't mention this, but most of our results would module some technicalities, generalize to higher dimensions. So what is next? I'll say stay tuned. These are coming soon. Thank you so much.
Great. All right. I don't claim I understand any of this stuff, but if anyone wants to say something, please, yeah, first, second.
So you say that you have a dictionary and you use quantum information as a tool to understand physics.
Have a partial dictionary.
A partial dictionary. But with this streaming compression protocol that you designed, can you take that back and say, sell this to Netflix and give them, hey, I have this way of compressing your data?
I'm not sure. What do you mean? Do you mean, are we going to use gravity to learn about quantum information theory? Is that what you're
No, it's your state merging streaming compression algorithm, something that you can implement efficiently and use commercially for something.
No. We're not claiming anything of that type. Definitely not. It's just a connection. It's some map between things that we recognize and love in gravity and some quantities that are entropic and appear in communication.
No, well, fuck, I have the microphone. Just wait. After gag protocol. Back in the last row.
Very short question. Thanks. So there are some approaches within the loop quantum gravity community to compute links for non-semi-classical treatments of gravity using things like spin networks and in terms of Casimir operators. And so I wonder do you think there's a way to make this work for low central charge theories?
So I have to first say that I do not know much about loop quantum gravity, so I'm definitely not an expert, so I can't comment on that part. But about low central charge field theories in the context of ADS-CFT, I can tell you that the consensus in the community is that ADS-CFT still holds, but the problem is that the gravity theory you have is definitely doesn't have a semi-classical limit, so we don't really know what we're talking about. So if we try to build a map, we don't know one side of the story. So we can't really say much. Although if you're interested, there's some effort in trying to make such a connection. It goes with names of like dual to minimal models in 2 dimensions.
Thanks.
So the streaming requirement is natural for Netflix, but is there some reason that in ADS-CFT that it's natural? Like you can't bring all the information together in one place to compress it at once, or anything like that?
I don't think that we have any intuition of it being natural. It's just seems like the result that gravity suggests. So that's the length of a curve. There's a one-to-one correspondence. That was sort of what was interesting to us.
I also have a totally primitive question. I mean, one of the things that we found interesting about the state merging is that the conditional entropy can be negative. In your case, it's the length of a curve, so it can't be.
Very good. That's an excellent question. We're confused about this for a very long time, but turns out that there's actually beautiful, the same way that it works in state merging works here as well. So in state merging, what happens is that if it's negative, rather than using up entangled pairs, you're extracting entangled pairs. Same sort of thing happens. So as you go along this protocol, you can't stop halfway in the middle and say this cost corresponds to length of the curve, partial length of the curve. You have to go all the way to the other side, and somehow these positive and negative contributions, they add up and cancel out beautifully. It's magic. It works. The total cost is always positive, with the exception of one thing. So, okay, so this is sort of the area, the length that we're talking about is somewhat directional. So yeah, it's a little bit technical. Anyway, yeah, but that works. There's no paradox over there.
Okay, cool. Anyone else?
Do you have at present any idea about how to build a resource theory of gravity?
This is something that I would like to say is work in progress. We're definitely thinking about it, but we're sort of blocked. So yeah, I don't have a. Maybe we could discuss afterwards.
Thanks.
Okay, I think it's time to thank Nima and all the speakers of today. And if I understand it correctly, we move directly on to the business meeting, which is